Good afternoon. My name is Cassandra Nabatanzi. I will be taking you through the first slides of our presentation. Our project is a graph-based reasoning and causal interference with large language models for student mental health screening at Makerere University. Our keywords for this project are mental health screening, large language models, knowledge graph reasoning, causal interference, student support systems, and higher education. Now, for the contents of this presentation, we shall have the introduction, related work, the problem statement, research questions and objectives, and research contributions, the methodology and system architecture. Then we'll have the dataset description, the results and conclusions, and then our anticipated limitations, counteraction plans, and references. Yeah, so the background and introduction to our problem. There's the rising cases of depression and anxiety among university students, and these university students have limited access to timely counseling and referrals. For example, the counseling office in Makerere University, most of the times it's closed. I pass by there most of the time and I've never found it open. Now, the current systems in place are fragmented across different university offices. You find that if someone wants a service, they'll have to visit very many different offices to find it. So we saw the need for a safe and explainable AI tool to support early detection of depression, of anxiety, and stress among these students. So our project basically is a mental health AI triage assistant. It uses graph reasoning and causal models to link stressors to resources. It also integrates with campus services like the Counselling Centre, the Deans, the Gender-Based Violence Desk, and many others that we can find. And our goal for this project is to screen these things early and to accurately handle them and work through them quickly. Now, related works or recent trends for large language models in healthcare, we've found a few chatbots, Warbot and Wiser, but they have limited causal reasoning and they're not very well grounded institutionally. They are not attached to any institutions. You'd have to know them to actually search for them. And for example, scales like the PHQ-9, the GAD-7, they're widely used and effective for depression and anxiety and stress detection in student populations. Knowledge graphs in medicine are applied for clinical decision support and they improve grounding, explainability, and error reduction. Now, causal interference in AI is an emerging trend. It integrates SCMs and DAGs for better prediction of risk trajectories. For example, if this person is stressed, what is the course of action they will take and what are they most likely to do? Yeah, and university mental health systems, what we discovered is that studies highlight gaps in coordination across services. They're very fragmented and reactive. For example, there's no streamlined process to take these students that have been discovered with problems through their problems. So you'll find that the services are scattered across different desks. And the trend is to shift towards explainable multimodal campus integrated AI to help these students with their well-being. Now, I will move on to our problem statements. There's rising depression and anxiety among students. The services to help them are fragmented and inconsistent. There's no multilingual support and there's also cultural limitations. And there's high-risk cases or missed and delayed escalation. So we need trusted and explainable triage that shortens the time to service across campus units. If a student shows up and they need help, they should be able to get that help quickly and effectively. Our computational problem is how we can fuse this heterogeneous data with policy-aware knowledge graphs and how we can do causal reasoning on stressors. For example, how can we reason out a person's anxiety, what is causing it, how can we help them solve it? There's also uncertainty about the fairness of these AI tools and low latency and private multilingual deployment. So we have very few tools that are integrated with different languages. Now, these are our research questions. How can causal reasoning with large language models improve screening and triage of student mental health needs? What role can a knowledge graph play in linking stressors to actionable referrals? And how effective is the system in ensuring safe and timely and explainable escalation for high-risk cases? So our objectives for this project are to build a knowledge graph for these stressors, to integrate models with large language model reasoning, and to develop a safety-aware chatbot for early screening and referral. Also to evaluate system performance on accuracy, fairness, and usability. Yeah, our research contributions would make the following key contributions to advancing mental health, AI-driven mental health screening. We develop a campus integrated mental health triage assistant. and we built the first policy-aware knowledge graph for Makerere University. We were also able to integrate safety-aware LLM models with escalation rails, and we evaluated the system using technical, clinical, and user experience metrics. Yeah, I think that is it for me. I'll let my teammate take over.
So I'm the one following. So first of all, the methodology here during the development of our model. So the architecture is the process we followed is pretty simple. From the data set, we selected input data, which was prepared for preprocessing, and then class imbalance and data handling was done with the preprocessed data. Feature selection, we select specific features that correspond to state of depression, for example, if a combination of specific features happen, detect depression states, for example, and try to predict the result and then task deployment. So we're going to show you some of the example of train model. So the data sets used in this project originate from a mental health survey conducted in the university from students, and it captured psychosocial and academic factors that may influence student mental status and their likelihood of seeking support. Here you can see there is an age distribution histograph which showed that most of the survey included 22 years old, between 22 years old and 24. We have a correlation which can help relate depression-related items to loneliness and maybe communication difficulty that can also deduct to depression problems. So after preprocessing prepared processing the data, here we used a stratified five-fold cross-validation to ensure fair evaluation across all classes. As you can see, the result of the random forest resulted in a F1 macro 0.691 to 0.093, and our XG boost resulted to the following result. So if I interpret this, the random forest performed better than the XGB on average. So the random forest also showed more stable performance, and therefore the RF was selected for deployment because it's balanced accuracy, robustness, and interpretation. Moving on, here we tried to create a readable report of the prediction and of the whole training of the model. So we have some result of the precision, the recall, and the accuracy of our model. So as you can see, the high degree of loneliness resulted in more likely chance of a depression stage. Moderate or low degree of loneliness resulted in a more higher precision or of not being in a stage of you can also see a confusion matrix that represents all that data. Moving on with the slide. Here is the highlight, the features that have been selected, that are the most important features to deduct if someone is in a stage of depression or not. So you can see most how most of them have been answered and in which amount of students. I won't go through it. Next, moving to the next slide. Now, this is some of the results we got from the model. So we took some features, connected them to loneliness level, which mostly represent a depression stage. So first of all, our result was compared with gender, which of the two is more likely to be related to loneliness levels, like with higher loneliness level. Also checked academic status to be compared with depression. If the person will work as well as study or relationship status, etc. And the result on the next slide can we can see a numerical correlation graph that shows those specific and how they connect to depression. Moving on. So which model have we used here? Here we used the XGB boost for specific region. First of all, as you saw in the performance, accuracy, F1 score, it provides better performance when it comes to prediction, get specific prediction. Scalability can handle large data set and categorical features. It's also robust because it handles missing values in balanced classes as well, and consistent, stable across multiple validation runs. So how did we proceed? As we said in the architecture of the model, data collection, we first proceed in data collection, survey responses stored in the document, in the data set we used, sorry, pre-processed by cleaning or encoding categorical response, scaling, etc. Moving on to the next slide.
Thank you, David. I don't know what has happened to Marvin. He was on
Moving.
and he was supposed to take the next part. Yes, Marvin, if you could please take us through the conclusions and limitations as we summarize. We have 5 minutes.
Okay. Let me go through the conclusion. Our project we're going to on. So right now we demonstrated a casual way of graph reasoning LLM for students, mental health. These are one of the conclusions we came up with. The system links stressors, risks, intervention, campus resources with explainable outputs. And well, this approach contributes to self-explainable and campus-integrated AI well-being. Some of the limitations included data availability and privacy. Data was limited, and most of the data is general. So it kind of an end project. And then computational constraints included deployment on modest servers, and this might limit scalability. Let's move on. Well, moving forward, the research can be expanded to strengthen its real world impact and adaptability across different contexts. The system has shown promise at Makerere University, but further refinements are needed for broader adoption, scalability, and inclusivity. Or the future works and recommendations can include, well, we need a data set that is multi-campus and national. We can incorporate real-time and data streams, and also we can expand multilingual support beyond Luganda and English, and also include other languages like Runyankole. And then also conduct pilot studies with counselors and students to refine usability. First, and then also we can explore integration with mobile platforms. That's it.
Thank you, Marvin. I think that brings us to the end of our presentation. We couldn't hear you at the end there. I think your network got bad. That's it from our group. Thank you. You're muted.
But I was saying, just send what the recording of the video. I'll just edit it.
Okay, let me send it.
Mm.